Hello everyone, thanks to everyone for watching this video. My name is Qi Dao. I'm an architect and engineer. Today's video is titled Prestressed Concrete, and it is going to provide you a broad overview of the prestressing and also the serviceability limit states. I'm going to give you an overview of what I'm covering today's video. First at all, we will have a look at some fundamentals of the prestressing, then move on to the analysis of section and loads, and the serviceability limit states, then wrap up with conclusions. The analysis and the design of prestressed concrete is a specified field which cannot possibly be covered comprehensively in this video. This video concentrates, therefore, on the basic principles of prestressing, and the analysis and the design of statically determinate members in bending for the serviceability limit states. In the design of a reinforced concrete beam subject to bending, it is accepted that the concrete in the tensile zone is cracked, and that all the tensile resistance is provided by the reinforcement. The stress that may be permitted in the reinforcement is limited by the need to keep the cracks in the concrete to acceptable width under working conditions. Thus, there is no advantage to be gained from the use of the very high-strength steels which are available. The design is therefore uneconomic in two respects. That weight includes useless concrete in the tensile zone, and the economic use of steel resources is not possible. Prestressing means the artificial creation of stresses in a structure before loading, so that the stresses which then exist under load are more favorable than would otherwise be the case. Since concrete is strong in compression, the material in a beam will be used the most efficiently if it can be maintained in a state of compression throughout. Provision of a longitudinal compressive force acting on a concrete beam may therefore overcome both of the disadvantages of reinforced concrete. Not only is the concrete fully utilized, but also the need for conventional tension reinforcement is removed. The compressive force is usually provided by tensional steel wires or stands which are anchored against the concrete, and since the stress in this steel is not an important factor in the behavior of the beam, but merely a means of applying the appropriate force, full advantage may be taken of very high-strength steels. The way in which the stresses due to bending and an applied compressive force may be combined is demonstrated in this figure for the case of an axially applied force acting over the length of a beam. The stress distribution at any section will equal the sum of the compression and bending stresses if it is assumed that the concrete behaves elastically. Thus, it is possible to determine the applied force so that the combined stresses are always compressive. By applying the compressive force eccentrically on the concrete cross-section, a further stress distribution, due to the bending effects of the couple thus created, is added to those shown in this figure. This effect is illustrated in this figure and offers further advantages when attempting to produce working stresses within required limits. Since the object of prestressing is to maintain favorable stress conditions in a concrete member under load, the working load for the member must be considered in terms of both maximum and minimum values. Thus, at any section, the stresses produced by the prestressed force must be considered in conjunction with the stresses caused by maximum and minimum values of applied moment. Unlike reinforced concrete, the primary analysis of prestressed concrete is based on service conditions, and on the assumption that stresses in the concrete are limited to values which will correspond to elastic behavior. The assumptions include plane sections remain plane, stress-strain relationships are linear, bending occurs about a principal axis, the prestressing force is the value remaining after all losses have occurred. Changes in tendon stress due to applied loads on the member have negligible effect on the behavior of the member. Section properties are generally based on the gross concrete cross-section. The stress in the steel is unimportant in the analysis of the concrete section under working loads, it being the force provided by the steel that is considered in the analysis. The sign conventions and the notations used for the analysis are indicated in this figure. Now we consider a member subject to axial pre-stress force. If section BB of the member shown in this figure is subjected moments ranging between Mmax and Mminimum, the net stresses at the outer fibers of the beam are given by these equations, where ZB and ZT are the elastic section moduli and P is the final pre-stress force. The critical condition for tension in the beam which for no tension, that is FB equal to 0, so that we have this equation, minimum pre-stress force required. For this value of pre-stress force, substitution in the other equations will yield the stresses in the beam under maximum load and also under minimum load. Similarly, the stresses immediately after pre-stressing, before losses have occurred, may be calculated if the value of losses is known. For example, the maximum stress in the top of the member is derived as these equations. It can be seen from the stress distributions in this figure that the top fiber is generally in considerable compression, while the bottom fiber is generally at lower stresses. Next, we consider a member subject to eccentric pre-stress force. The stress distributions will be similar to those in the previous part, but with the addition of the term plus or minus P times E over Z due to the eccentricity E of the pre-stressing force. For the position shown in this figure, E will have a positive value, so that we have these equations. Note that as the pre-stressing force lies below the neutral axis, it has the effect of causing hogging moments in the section. Because of the critical condition for no tension in the bottom of the beam, we can obtain this equation. Minimum pre-stress force required for no tension in bottom fiber. Thus, for a given value of pre-stress force P, the beam may carry a maximum moment of this equation. When compared with Mmax equal to P times ZB over A for an axial pre-stress force, it indicates an increase in moment carrying capacity of P times E. The maximum stress in the top of the beam can be derived as these equations. This equation is the same as that obtained in the previous part for an axially pre-stressed member. Thus, the advantages of an eccentric pre-stress force with respect to the maximum moment carrying capacity of a beam are apparent. Next, we will introduce the design for the serviceability limit state. The design of a pre-stressed concrete member is based on maintaining the concrete stresses within specified limits at all stages of the life of the member. Hence, the primary design is based on the serviceability limit state, with the concrete stress limits based on the acceptable degree of flexural cracking, the necessity to prevent excessive creep, and the need to ensure that excessive compression doesn't result in longitudinal and micro cracking. For a single span, simply supported beam, it is usually the minimum moment at transfer and the maximum moment at the surface that will govern, as shown in this figure. From this figure, the governing equations for a single span beam are expressed here, where Fmax dash, Fminimum dash, Fmax, and Fminimum are the appropriate permissible stresses at the transfer and serviceability conditions. PL is the pre-stressing force at the transfer, and K is a loss factor that accounts for the stress losses. For example, K equal to 0.8 for 20% loss. A useful approach to design can be developed if the equations are treated graphically. These equations can be arranged into these forms. These equations now express the linear relationships between 1 over PO and E. The relationships can be plotted as shown in these figures, and the area of the graph to one side of each line, as defined by the inequality, can be eliminated, resulting in an area of graph within which any combination of force and eccentricity will simultaneously satisfy all four inequalities and hence will provide a satisfactory design. The lines marked 1 to 4 correspond to these four equations respectively. This of construction is known as a Magnol diagram. The Magnol diagram is a powerful design tool as it covers all possible solutions of the inequality equations and enables a range of prestressed force and eccentricity values to be investigated. Values of minimum and maximum prestressed force can be readily read from the diagram, as can intermediate values where the range of possible eccentricity for a chosen force can be easily determined. From conclusions, what we learned: prestressed concrete is a form of concrete used in construction. It is substantially prestressed compressed during production in a manner that strengthens it against the tensile forces which will exist when in service. Prestressed concrete is used in a wide range of building and civil structures, where its improved performance can allow for long spans, reduced structural thickness, and material savings compared with simple reinforced concrete. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.